And let's get started then. So, welcome everyone. January 14th, Thursday, 2:15, time for the ninth episode of Elements of Machine Learning. Last week, I was already looking very much forward to explaining to you kernels, because that's basically where we left off, right? I mean, that's and I thought we were going to do this today. Well, I'm sorry. I mean, that is not what the book had in mind for you, and that it would have been, I think, a very natural step to go from kernels then to kernel machines. But we're going to go a little bit deeper into nonlinearity in a slightly different way. And essentially, what we're going to do today, you could say, we're going to do step functions on steroids, right? I mean, that we're really going to push the step functions to the max. To the point that they actually become useful in that. And a step function on steroids, that's a tree, a decision tree or a regression tree. I mean, not one of the trees that you have outside, but it's a proper computer science tree which is grown upside down, in that, as you also know from search trees and all that. Good. Let's see. Today is also the day that we're gonna, or this week is actually the week that we're gonna be evaluating EML. So somewhere halfway the course, when we hopefully have maximum attendance, I'm going to share with you the links to the evaluation forms. I'm going to ask you to fill them out and blah, blah. But I mean, details about that will come later. It's not so important just yet, but just that you know, right? I mean, there's going to be some excitement in a bit. But let's first go into what we're actually planning to discuss, and let's learn something, hopefully. Okay, first things first, what is a decision tree? What is the basics? I mean, a tree, a bit like a search tree. I mean, it's really not that different. It decomposes a data space into regions. So in a search tree, you will make decisions. I mean, is something larger or smaller, right? And then you go deeper and deeper, closer and closer to the actual node or element in your array that you would like to return. Slightly different, but still quite similar in that. What we're trying to do right now in a decision tree is that we're going to have a tree that has deciding factors. I mean, here we have an example. So here we have the example of the tree. I mean, for the hitters data set, I mean, sports people that make way too much money, right? I mean, it's just an example, doesn't matter so much. And every node in the tree, so this is the root node, has a binary decision. So it's a binary tree. In theory, we can also have multiple decisions. You have a ternary, whatever tree, right? I mean, that's as much as you can count. But for practical purposes, to keep things somewhat tractable and interpretable, we typically focus on binary trees. So here the first decision is that, is this person, or has it been, what is it? Yeah, how many years has this person played for this, perhaps team or perhaps professionally? If it's less than 4.5 years, we go to the left branch. Otherwise, we go to the right branch, right? If we go to the left branch, then here in this case, we already end up in a terminal node, and that's so a final node. There's no further decision. It's also called a leave, obviously. And here in this particular case, that means we immediately have a decision. Well, this actually is a regression. So there's just the value that if you have played for less than 4.5 years, the best guess of this model is that you make the salary is, well, it's 5.11, well, e to the power 5.11, right? I mean, why make it interpretable if you don't have to? That is the expected salary if you have played less than 4.5 years. If you have played more than 4.5 years, or at least 4.5 years, then you go into this branch. We hit now another internal node, another decision, and depending on how many, well, in this case, balls you have hit, you go to the left or the right node, and there again you have an estimate of an average salary, right? And that, so what have we now done? We have decomposed our data space into regions, right? I mean, 3 regions in this particular case, 1, 2, 3. Each of these regions, we have one constant model that predicts what is going to be happening there, right? So that's, in this case, the average salary. And you can imagine that, well, as we will see a bit later into this lecture, it doesn't just have to work for let's say, an average salary. So this is, let's say, R3, this corresponds to this value here, R2 corresponds to that value, R1 to here. We can do exactly the same for classification. And we just have what is the majority vote. So if under this condition, we're going to have many people that, I don't know, let's say, okay, have ginger colored hair, right? I mean, that's versus black or whatever other color, then this would be the majority vote. So the key aspect of a tree model is that you have regions that you identify by choices, binary choices, and within these regions, the decision is constant. So that is the main idea. Okay, now, one of the key advantages of decision trees is that they are very easy to interpret, right? I mean, especially a very shallow tree as we have here. You know, it's relatively easy to see what is going on. It's easy to check. Does the model make, well, any really stupid mistakes, right? And that's, or is there something funky going on in my data? Because of course these trees are not drawn up by a human, but we have algorithms to find them. You can very nicely graphically interpret them. So you can also have, like I said, the lengths of these branches. I mean, you can depict them differently depending on how large are the differences in the node decisions and whatnot. I mean, you don't really have to, but you can. And hence people typically say decision trees are very interpretable. And this book goes along with it, but they didn't count on me because I personally, well, I agree, but I don't agree. So really said, this cute little tree here is definitely interpretable. And you might even say that if you have a cute little tree, it mimics to a certain extent human decisions. That, for example, the emergency ward at any, well, self-respecting hospital, when you come in with some, let's say, chest pain or whatnot, they use these types of charts, right? You could call it a decision tree to determine, okay, is this person really at risk of heart failure? Or, well, did they just eat too much too quickly and, okay, just sit down and we'll be with you in a minute, Mr. or Madam. So it's really also a quick check. Okay, is this person out of breath? Is there like pressure on chest? Is it this? And if not, okay, well then, or if so, then the risk sort of diminishes when or is categorized. In many other decision-making processes, I mean, you first, okay, well, is this the case? Yes. Okay, well, then we go deeper. Then we have another condition, and then, okay, if not this, then maybe that. This is exactly what a decision tree also mimics. So as a model, it fits human decision making and understanding very well. Now, I'm already hinting ahead at what I'm going to be saying later and showing later in this lecture today. Decision trees very quickly can become extremely difficult to read and essentially as unexplainable and as uninterpretable as possible. And that's basically, we as humans are pretty decent. Okay, if somebody has played less than so many years, yeah, okay, not so much money, more, but they don't hit as many. Okay, that's this, right? So there's essentially two decisions to keep in mind, and we can do that, right, in our heads. You can already imagine if we have like a whole stack of such decisions, right? So if like on an odd day and it's sunny and yesterday it snowed and my car was parked there, and so way too many conditions, right? Yeah, then of course it is possible that some certain event may or may not happen, but we're overfitting, right? I mean, that's, but sometimes we're not overfitting. Maybe we have plenty of data, but it does not become easy to understand what the hell this model is after, right? I mean, that, so small decision trees, interpretable, yes. Big decision trees, right? I mean, very deep ones, not interpretable at all, right? That, and in many research papers these days, we're all after explainable AI, explainable machine learning, and many people then immediately point to decision trees as being the explainable type of model. Typically, these are people that never really looked at a decision tree. So I want to immediately point this out, right? Immediately should, let's say, in our own EML foot. Decision tree is very explainable, except when they're not. Okay, good. Now, having said that, and giving some examples a bit later on, let's look into how to build such a tree. I'm particularly interested in regression trees right now because it fits a large part of the lecture, but almost all that we're going to be doing in the next few slides can immediately be applied to classification. And I'll show you how to do this also in a second, right? I mean, so how can you think of what our decision trees actually doing in that sense? They're doing something like this, but not quite. We build it up, right, as a didactic example. In that sense. The idea of a decision tree is that in our input space, so over x1 and x2, we're going to define regions, and in each of these regions, we're going to have a constant decision, right? I mean, that's it. Now, what is a region? Well, a region is just a box, right? I mean, that's, and as you see, okay, here we just drew some funky boxes, right? So what we're saying is that in this area, there would be, let's say, one value predicted. Here, also another value. Here, another value, and so on and so forth. This is one way how we can draw a set of boxes on top of each other, right? A set of constant regions. That is exactly what a tree tries to do. It tries to divide the predictor space, or the data space, into J, disjoint regions in that, and within each of these models, a constant, and each of these regions builds a constant model. Now, in theory, these regions can have any shape. Here, they're boxes. They could be circles, they could be whatever, right? I mean, that's a go wild, and that's they could be dragon shaped for all I care. Except that, well, then we don't really have a tree. The tree doesn't really represent this very well. So what we do in practice, we restrict ourselves, the language in which we can define these areas, to rectangles. That already disallows these partial overlaps, right? I mean, that's because now it just really needs to be, well, not squares, but rectangles. Rectangles is also too difficult. If you really want to explore all possible, let's say, sets of rectangles that cut up your space, you're not in for a good time. There's let's say too few restrictions. We need more restrictions, right? We need a leash. What is the leash that we use in decision trees? We use guillotine cuts, or rectangles that have axis orthogonal cuts. What does it mean? That we have, for example, this T1 cut here, right? I mean, that's this cuts the data space. This is the first one, like this, right? I mean, that's all the way to the top. That basically means any value below T1 that goes into one branch, any value above T1 goes into the other branch, right? I mean, that is the relation. Now, if we go into the left branch, so that means that we're in this space over here, we can now, and we only look at this data over here. We ignore this data. This data doesn't exist for all we care, right? Now we try to find that split, such that, I mean, let's say these are the people that make a lot of money, these people make not so much money, or these are lots of black dots and these lots of white dots, or whatever color you like. And then T2 would be the condition on X2 that splits that best, right? So essentially every node in the tree makes a decision on one of the input variables. And by just really having a lower or equal or higher than equal kind of decision, it cuts it guillotine-wise. Essentially, actually, it cuts it from left to right in this particular case. So this would be the first one. This would be the second cut. And well, in this particular, the tree that represents this model, in the left-hand side, we don't have any further cuts. We may have then the third cut that considers all this data. So basically blocks R3, R4, and R5. And maybe the best way to cut this one further up, such that here we have, let's say, the low earners, and here there's many more high earners, that could be again a condition on X1, right? And that's so in the right-hand branch, we again split on X1, and now we have the part, let's say, larger than T1, but smaller or equal than T3. And this is then larger than T3. In that right branch, we can again find some condition on one of the variables, in this case, again on X2, and hence it's axis orthogonal, there you are, right? So we very effectively restricted ourselves. I'm going to go back 2 slides, right? From drawing, well, I don't even have a slide for arbitrary shapes, right? This is sort of arbitrary boxes that can overlap, right? We would like to have that. That would be awesome, right? It would be a very powerful model, but there's no easy way of representing this, interpreting this and whatnot, right? And that's, so we don't allow this. Boxes that don't cut each other, already better. Still, too many degrees of freedom, right? Very difficult to define this and form this. And these guillotine cuts, they actually allow this very natural tree shape, like all this if-then-else type of decisions. Okay, now, how do we find these cuts, these T1, T3, 2T, and so on and so forth in that time? We would, of course, like, for a given problem, to find the best tree, right? I mean, that's the bestest tree, perhaps even. Now, what is a bit unfortunate is that if you choose not a completely trivial objective function, then learning the optimal tree is NP hard. It's not going to fly, right? That I have this here in a reference. I mean, that it's already been a result been long known, right? I mean, that now the good thing about NP hard problems is that it gives us an excuse to, well, just try something that is not completely stupid, right? Which is essentially what we say is a heuristic, right? I mean, we just try our very best. We know that the best solution is unattainable, I mean, or at least it's unverifiable that we have found it, right? We might have stumbled upon it, but we don't know for sure. So we're just going to try our very best. That's our very best in decision tree learning. Now I need to be a little bit careful in what I say. I mean, that's, let me just say, it is, for all practical purposes, what I'm going to explain to you next. However, small aside, in the last really few years, 2, 3, 4 years, something like this, there have been a few small breakthroughs, right? I mean, that's and for specific instances, we can actually learn optimal trees, or actually even without the quotes, but we can learn optimal trees within reasonable time, right? But for specific instances only, right? Do you know beforehand if you have such an instance? No. So for all practical purposes, we're just going to do what I'm going to teach you, right? So overall, what we want to do, we want to minimize the training error. That makes sense in that. So what is the training error here? And the nice thing is this is almost the same between the regression and the classification problem. We're going to sum, first and foremost, over all J regions that we have, right? So we have RJ regions. I mean, these are each of these boxes, right? I mean, and now for all of those boxes, we go over all of the data points that fall into this box, right? And because if a data point falls here, well, we would predict its value using R2, right? I mean, that's R1, 3, 4, and 5 have nothing to say about the data point that falls in R2, right? That is one of the strengths, also the weaknesses, but mainly a strength of a decision tree or regression tree. So how do we predict any point in R2? Well, by looking at what would be the value in R2 and what is the error that we then make, what is the actual value, what is yi for that particular point, right? I mean, and how far away is this from the average value in RJ? That would be the regression case. In the classification case, well, it's slightly different, but it comes quite close. And we take the squared error. So this is just standard squared error, where for every point, we just figure out in which box would we use to make the prediction, and then use that prediction. Okay, now, like I already said, it's computationally infeasible to find the bestest tree. So we're going to do this greedily, in this particular case, right? I mean, I said we're going to use a heuristic. Well, heuristics could be anything, but greedy is very often a very good approach. And not always, but very often. Also, greedy strategies very often allow for guarantees. So not a guarantee in the sense that you know that you have found the best solution, right? Otherwise, the problem would not be NP-hard, right? If you just at each step take the best step and then you find the optimum, then it's not NP-hard. I mean, that's just by definition. However, what you can often, for many problems, say is that if you do at every step do the locally best thing, then you can often give proofs on how far can you possibly be from the best solution overall, right? And this strongly depends on the structure of the problem. Let's say, is it submodular? Is there a law of diminishing returns or whatnot? If that is the case, if the problem is submodular, then a greedy approach often brings guarantees. Decision tree land, typically no. I say typically because, again, we can find some let's say, definition of training error for which it might work, but in general, no, right? So what we want to do, if we want to, so this means basically that we're just using greedy in the hope that it will be good, and as you will see, it quite often is. But we're not after guarantees right now. What we're now going to do, starting from an empty tree, which basically is just one big box, right? I mean, that's so without any of the inner lines here, we're going to find that currently, here we write apparently, but let's say the currently optimal split, right? So which is that line that we can draw starting, let's say, from the axis of x1, right? I mean, so basically out of all vertical lines, right? And we consider every horizontal line, all individually. And for all of those lines, we're going to see which would lead to the maximal decrease in training error, right? So which of those lines leads to the best value over here? And that line, once we have it, well, we keep it, right? I mean, that would in this case be this T1 line. And then we do the same thing, except that right now, well, we can either carve up this space by looking at all of those lines, or by looking at all of the horizontal lines within this area. That is for the left branch. At the same time, you could say in parallel, we look at every possible split of the right-hand side, again by a vertical bar or by a horizontal line, right? I mean, and out of all of those, we again take that one that maximally decreases the training error. And again, and again, and again, until we hit some stopping criteria. So, okay, I put this a bit more formally and a bit less with my virtual laser pointer. We recursively split any leave, such that we minimize the training error, choosing an appropriate predictor xj, right? I mean, that's out of all of those that we have at our disposal that we're allowed to touch, and, well, trying to find that split point S. Now, what I just said, that we consider every possible, well, vertical or horizontal line, right? I mean, or if we have a 3D, if it's also X3, then there would also be the spokes, right? And so on and so forth. Well, there are, of course, infinitely many of such lines, right? And that you can contemplate many of them. However, luck is on our side, in the sense that our data is finite. We only have so and so many data points. And suppose that we have two little data points, right? Two cute little data points over here. And I want to split, right, between them. Let's say this is a red one, this is a blue one, right? I mean, that's, and my task is to predict redness or blueness, right? I mean, that's, then, hey, isn't that cool? Any line that I draw between those, any out of the infinitely many lines, will have exactly the same effect, right? If these are the only 2 points, if there would be a third point over here, okay, well then any line here, right, or any line there will have exactly the same effect. Which of those lines doesn't matter. Doesn't matter at all, right? And that, so typically what we just look at is just that line smack in the middle. That basically achieves this maximum distance between these 2 points, right? That's, is this, let's say, a hard rule? Is this the best thing you can do overall? No, because after having chosen such a line, well, after, let's say, having chosen this line, the next step okay, I need another color pen. Black on black doesn't work. Okay, then we would have to choose this line, right? I mean, that's, and maybe if I would have chosen this one a bit more here, then I could have just caught one more thing a bit higher up. It would have been easier to make a certain split, right? So it's a heuristic. It's heuristic, right? I mean, that's, I personally like heuristics because all of a sudden I'm relieved of the pressure of being perfect. And even though, of course, I strive to be perfect, I also like it now and then to be scruffy. Okay, good. So that is how we choose the appropriate split points. And you can imagine many algorithms that can also cut more corners to be faster. But overall, what we do is we minimize. For every line that we draw, what we want to have is, so suppose that we now, yeah, actually, so that's, I mean, I need to update these slides. I need to remove all those lines. We just have an empty square, right? I mean, that, and now, well, for example, if we contemplate this line, the T1 line, right? I mean, that, basically, how do we decide, would T1 be a good decision? Essentially, what we now want to evaluate is, okay, what is the error that we make on the left? And what is the error that we make on the right? Because together, that would be the new error from the final, for let's say the new model, if we were to introduce that split. Okay, good. And here, as the training data set is finite, only a finite number of choices, meaning that splits are placed halfway between training points, like just said, right? That this works very well with training data. For test data, I mean, yeah, then it might be that the test points are just, let's say, well, just a bit to the left or too much to the right than you would have liked to place the point or the line, but okay. Something's got to give. We keep on finding these split points and these lines, right? I mean, so recursively carving up our space until a stopping criterion is met. I already said a few minutes ago. For example, and this is what many algorithms do, until there's no region with more than k points. Here on the slide, 5, right? But you can imagine that if we have just one data point in a region, there's little point in splitting it further, right? I mean, that's so that is a very natural, let's say, moment to stop. But only one point in a region, no, that's very high variance, right? I mean, that's that's a bit too brittle. I mean, so perhaps you want to have a few more data points in a region. 5, like here on the slide, is completely arbitrary. You could say 10, you could say 100, whatever, right? The more points you have in a region, in a way, the better. Because, well, the better you can estimate what would be the value in this region. But also, the more points you have, the worse. Because maybe this region actually now has 2 populations, right? I mean, high earners and low earners, and well, that is exactly what you want to split. So, yeah, well, how many is always difficult to say beforehand. But, how to balance, how far to split. We will see a few other methods, particularly for the classification problems, that help there a lot. But typically you want to set a minimum number of points per leaf just to avoid statistical instability. Luke asks, can we do cross-validation for the stopping criterion? Yes, of course. I mean, any parameter we're going to estimate with cross-validation. We'll also see this in a bit, indeed. That so you can try to use cross-validation to prune your tree, but we're not there yet. Okay, so. What we have here is a visual depiction of the example we've been working on here on the right. The decision tree corresponding to these set of boxes is this one over here, right? X1 smaller or equal than T1. Okay, that is then we're in this large thing, right? So this means at this node, internal node, we have another decision carving it up into two spaces, respectively R1 and R2, and so on and so forth. This here is now the 3D depiction, like for each flat area corresponds to one of these R boxes, and the height of that box or of this plane, that is the value that we would associate with this box. So if this is R1, for example, R1, yeah, seems to be R. This should be R1. Then, well, this is actually no, this is R2. This is R2. This is yeah. R2 has the lowest value. R1 a slightly higher value. R3 already much higher, and then to the right of R, and so on and so forth. Right. That, okay. Now, what we typically do, and there's very good reasons for that. I mean, that the theory part I'm going to skim over because that goes a little bit too deep for EML. But typically, we grow a tree until, well, the stopping criterion of, I mean, so and so many data points hits, right? I mean, that, or if splitting any further doesn't make any sense. You can imagine that if this is not a regression problem, but a decision problem, let's say this R5, there's only blue points here, right? I mean, and let's say we wanted blue and red. That's what we want to classify. But if we have a region that is just blue, there's no point in introducing any further splits anymore, right? I mean, that, so then we can also stop. That, same thing in a regression problem. If you could say, okay, hey, the variance within a bin drops below a certain value, right? I mean, that's then essentially there's no point in splitting any further. That, those are, let's say, additional signal that you can use. Now, but if we keep on growing until there's only a very few data points in every leaf, we'll have a highly overfit or overtrained tree, which is bad, but also good. That's, and we're going to see how. So there's two things that we can do, how to avoid this, right? I mean, that's, and in the second one, I'll show you why it's a good thing to first grow fully. So the first, let's say, knee-jerk reaction you might have is, okay, well, let's not grow our tree too deeply, right? I mean, that's because then small trees are more interpretable. That's what we just said. And I mean, we don't overfit as much. Okay, that makes sense. However, this first variant is suboptimal because we're just heuristically, greedily trying to find these cut points, right? I mean, that, and it may well be that in the earlier iterations, we're just carving up the space very crudely, and then only afterwards we can see the actually good regions, right? They only become accessible after a while, and yeah, well, those are automatically the regions that we have down in the tree. So that means that if we don't allow the tree to grow deep, we're never going to get the good regions, right? And that, so growing the tree incompletely, if you do this too aggressively, if you say, okay, I only allow, well, 2 or 3 levels, right? I mean, that's decisions. Yeah, well, unless you have somehow magic knowledge of how complex your problem is and how optimizable it is, yeah, you might not enjoy the result. But, as we put it here, greedy procedure lacks foresight, right? I mean, that's, it may make stupid decisions early on that only later on it can fix. This is why actually just first blindly learning a tree to the best that you can, becoming overfit or very overfit even, this may actually lead to a good result if afterwards you prune. So we first grow the tree, right? I mean, we include, let's say, too many internal nodes. And then after we have done so, we're going to kick out nodes. Now, intuitively, you would say, okay, but which nodes would you kick out? The ones probably that you added last. That may be, but it doesn't have to be. And it's the doesn't have to be where the magic happens, right? I mean, it could well be that actually we remove one of the earlier splits, What does it mean to remove a split? It means that, okay, well, all of a sudden, let's say these two branches, they merge again, right? I mean, that, now, so let me, before I continue, just to point out, I mean, how can we now measure how good is a tree, right, in this pruning procedure? So of course, we want to optimize the test error, but not just that, we want to balance this, because if we just optimize the test error, okay, cross-validation comes into mind, but it becomes super expensive. If we optimize the training error, that's what we did. That's where we got the overfit tree from. So let's now try to keep into account the complexity of the tree, of how many splits do we have, right? So does a split give a significant, I use air quotes because we don't use an actual significance test. Does it give a significant or like a really big contribution to the performance of the tree? So what do we typically do is something along the lines of, well, what we also do in Lasso. I mean, that, so we have for all internal nodes, and that's and then for all points in each of the leaves, we measure the sum of squares. Okay, fine. And look, we have a penalty term, regularization term, which looks at, well, the size of t, which is the number of internal nodes, or the number of leaves actually in this particular case in the tree, times magic value alpha, right? That's I call this magic value alpha because, okay, how should we set alpha? Well, let's try it. We can always try cross-validation, of course, right, to help us set it, but nobody knows. What is now the let's say the effect of alpha? If we set alpha to 0, then obviously we'll get a super overfit tree, because we just want to maximize or minimize the training error, right? And not, now if we set alpha higher and higher, then obviously the number of leaves that we have, right, the number of decisions, because the number of leaves is essentially, well, yeah, okay, there you have it. It's related directly to the number of leaves. Number of nodes, number of leaves are directly related. The higher I set alpha, the more emphasis I give to having few nodes, right? I mean, that's in my tree, few decisions, few leaves, and hence having a simpler tree. So the higher the alpha, the more, let's say, the better a split needs to be before we allow it into the tree, right? And that it's a bit like with Lasso. And if you there have set your learning rate really, or it's your alpha or your lambda, or whatever your Greek letter you use, if you set this really high, then you also constrain very strongly. You want to have very few predictors, right? Exactly the same thing is happening here. Okay, yeah, and whereas we call that shrinkage, right? I mean, that's in the regression case. Here, alpha literally shrinks your tree because, well, you get a smaller tree, right? You have fewer splits. So hence, whenever I reach shrinkage, I always need to think of trees and not so much of ridge or lasso. Okay, yeah, there we are. So what do we now have? The basic algorithm is that we first grow a full tree using just recursive binary splitting, typically using some, let's say, well, very basic stopping criterion, like number of data points per leaf. Then using a cost function like this one, I mean, you have many different ways on how to define this complexity term, right? Just counting the number of leaves as one. There's more refined ones that we already seen a few, and we might see a few more later on. And then, well, use cross-validation to choose alpha, just to figure out, okay, I mean, how complex a tree should we actually need, right? I mean, that, and then overall, I mean, we can figure out what would be a good alpha by just looking at essentially the error plot, finding the elbow, right? I mean, that value where it's sort of the one standard error rule, where a more complex tree does not really give a significant gain. That's the alpha we use. We learn a tree for that, and there we are, right? That is going to be the final answer. Good. Let me see. There's a question. Is it possible that while pruning some parent nodes get kicked out, or would it kicked out always be leaves? That depends a bit on your algorithm. So the simplest way is obviously to only allow kicking out the leaf nodes, right? I mean, that's because that means that we have two regions that are already adjacent that we just merge again, right? And that if you want to remove an internal node, let me go to over here, right? I mean, so let's see, let's consider first removing this node, right? I mean, that's what would that mean, right? That would mean removing this split, and that mean that these two boxes, R4 and R5, just become one box, right? R4 prime or something like this, right? I mean, that's basically they go back to what they used to be in that. And then, I mean, well, an alternate pruning step would be to reconsider this one, right? That would be removing this split. Okay, that is easy peasy, right? You can see immediately how this works. Now, there's nothing holding us back from immediately removing, let's say, this split over here, right? I mean, why not? However, we do need to decide if we remove this split, what do we do with this guy over here, right? So this split means this left-right split, right? And that's one thing that we could do by removing this one, we can level up this one here, right? So basically, let me take it back. We can remove this split, which is this one, and that means that we just basically prune away the entire left branch, right? That is one thing how you can imagine it here. What does it mean? We remove this one, and immediately we also remove that one, because then we have one big box, right? And everything works again, right? I mean, that's basically the magic is we need to get back to boxes, to an admissible model that we can represent as a tree, right? And that's one other option, removing T1, would be to continue splitting T2 like this, because then we still have a model that works. Why? Well, then essentially this split over here becomes the root, and this one over here goes, well, essentially over here. Right, that's normally I would do this on the whiteboard, and that's right now online. This is a bit more tricky, but just imagine removing this line and continuing this line, right? The tree model for this would be, one of the possible things would be first split here. So T3 becomes the root node. Then in the left branch, we would have T2 as the split, and the right branch, we would have this as a split. So now all of a sudden, we did manage to remove an internal node. But you already saw this involves choices. Which of the possible rewirings are we going to choose? And yeah, there you want to keep things as simple as possible. So it really depends on which particular decision tree learning algorithm do you use. And in practice, if I were to re-implement this myself very quickly, I would only consider removing the leave nodes. That's just out of laziness and well, let's say, keeping fingers crossed, hoping that the answer is a good heuristic still. Good. Okay, let's see, where are we? Yeah, building a regression tree, this we worked out. Yeah, so actually, I could have also gone to the to this slide. I mean, that's yeah. So the weakest link pruning. I mean, that internal node, if we collapse it, that causes the smallest increase in training error. Essentially, what we just said, right? I mean, that's so basically the increase in error that we get. Yeah, well, we don't want to increase the error, but if the increase in error is lower than the decrease in the penalty, right? So basically, the cost for having an additional split was more than having the small increase in error. Okay, then we're good, right? And of course, just like we grew a tree from, let's say, one node to many, well, too many, right? Just like that, we can do it now in the pruning phase. We can go from too many to, well, essentially too simple, right? And then if we just simply draw over that, let's say, over the pruned trees, what is now going to be the error, right? And we have the training, cross-validation, and test. Then we can just, by cross-validation, choose what is the best tree. So just standard, right? I mean, there's nothing that should surprise you. And well, if you have an overlearned tree, it's going to look like this. This is actually a perfect example why I say that a decision tree is not necessarily interpretable, right? I mean, that first split, so far so good. RBI, I don't know what an RBI is, but yeah, let's say number of hits, so far so good. But then if somebody has been playing more than 4.5 years and has had more than so many hits, but fewer walks, or more walks and then fewer RBI than this, and then more years than that, I mean, what are we talking about, right? I mean, that's I can't keep track of that. So just as an example, decision trees, you can explain them, but they're not necessarily interpretable. So they're a good friend for everybody who likes explainable AI, but not necessarily your best friend. Although don't ask me who your best friend is going to be. I don't think anybody knows the answer yet. Good. So far we were looking into regression trees, right? Each region we just spit out the average, right? And that's if we now want to do classification with the blue and the red nodes, I mean, what changes? Almost nothing. Almost nothing. I mean, that's prediction inside the region is now just going to be, well, the modal class. What the hell is the modal class? That's just a majority vote, right? Per box, you just count. I mean, well, how many do you have of each color? And well, the minimum error prediction is going to be the majority vote, right? If there's more red balls in your box than blue balls, you're going to say, okay, if a query point has the conditions for this box, I'm just going to say it's a red point, most likely, right? Just maximum likelihood. How do we now grow a tree? Very similar to how we did this previously, except that we don't have mean squared error, of course, right? I mean, that's we're going to use, for example, misclassification error. We want to now iteratively find those splits in the data such that, well, the predictions within each box are more and more correct, right? I mean, that's we want to avoid errors. That would incur a loss function that looks like this. So yeah, basically, so per, what is it? Yeah, in a region, this is notation is horrible. I mean, sometimes the book is great, sometimes it's horrible. So the fraction of points in region Rm that belong to class K, yeah, you always assign, of course, the majority class, right? I mean, that means that the proportion of the majority class in region M, that is the, let's say, the maximum correctness you can get, right? I mean, that's, and hence, if you now take this over the maximum overall, then you achieve it, your error. Okay. Horrible notation, but I mean, that one I didn't choose. I mean, that's, and I rather stick close to the book than exposing you to my variant of the notation that I think is more interpretable, and then you have to match it to the book, right? But now, one of the problems is that misclassification error, it's not, well, you would say it's not sufficiently sensitive. That is true. That's a very good way to phrase it, but I would say it's not informative enough. It does not inform us well enough what would be a good model, what would be a bad model, or let's say, are we on the trajectory towards a good model, right? That's there's many cases where misclassification will not give us any information. I mean, that's, I'll show you in one of the next slides. So one of the measures that people use in practice is the Gini index, or cross entropy, which we'll see on the next slide. What is the Gini index? It's a bit more soft. We can immediately actually show it here. So Gini index is what we're still discussing. Soon we will discuss the cross entropy. Now, if you look at what is the learning signal that you're going to get, right? So if you move a decision boundary a little bit to the left or the right, and that depending on the proportions, what is how bad is it? Now, if you have a box, a current region, where it's really 50-50, it's a binary classification problem, right? I mean, it's 50-50. It's pretty much the worst you can get, right? I mean, that because you can't really say is it now red or blue, right? I mean, that's perhaps it's purple. Misclassification error, entropy, and Gini, they all agree that probability for 50-50, they give the highest impurity, right? I mean, that's they're the most unhappy, they're the least happy, right? I mean, that's and during learning, we're trying to make these scores happy. We're trying to find a happy little tree such that in each of these regions we have the least impurity, right? I mean, that's what we want to find. Now, as you can see, misclassification has this, well, it's like a roof, right? I mean, it's very straight in that, and hence misclassification doesn't really care, because this is a straight line, right? I mean, there's no curve or anything, whether we have still, let's say, whether we go from a 50-50 split to a 49-51, right? It's happy, right? I mean, we gain something, yay, right? One, so we just go a little bit on this line, right? I mean, that's there's a bit of, let's say, gain. Or we go from, let's say, from zero error to one error, or from one error to zero error. It's equally happy because, hey, we gained one error, right? I mean, it's a linear line, right? I mean, that's so one error more or less, it's always, it makes it the same amount of happy. Gini and entropy, they're not the same amount of happy. In that, the difference between having a 50-50 or a 49-51 split, that's around here, right? I mean, that's, as you can see, there's almost no difference. And so the lines for entropy and Gini, it's almost flat, right? I mean, if you look at the derivative here, they're basically essentially equally unhappy, which is a good thing. Because if we have a pure 50-50 split or a 51-49, yeah, well, right. I mean, that's not really what I would like my model to go towards. Whereas when our entropy and Gini, when they're the most happy, here at these edges, right, when we can really remove, let's say, the final impurities from our decision model. So Gini and entropy are very happy when we can go from well, let's say 99, is it? Yeah, 99 1 to 100 0, right? We can really sort of remove all the errors. And then, yeah, now we have the perfect model, right? That's they're happier if you can make that step than if you can just, well, around 50-50. That's which is a good thing, because around 50-50, I mean, who cares? And near the end, so let's say the final bits weigh the heaviest. That is exactly where Gini and entropy favor. Okay, now back to the definition. How is Gini defined? We look at this proportion of the, it was the kth label for region M, right? I mean, that's, and we now do this, take the product to the proportion itself. I mean, that's, so it's really like if the proportion in this region is 50-50, then we have 0.5 times 0.5, right? I mean, that's 0.25. We sum this over all labels. Okay, that is the least happy Gini. I mean, that, whereas the moment that we have a completely pure Gini, then one of these terms, actually, well, then the proportion will just be 1, right? I mean, so it will be 1 times 1 minus 1. Hey, that is 0. And because of the product between these two things, it will go down very rapidly. That's why it gets this nice roundish shape, right? That's yeah. So Gini is the average training error. Okay, good. That's and overall, if we sum over all the classes, then we call it the Gini index. Don't ask why people chose that term. I mean, I wasn't around when the decision was made. I personally prefer not Gini, but I prefer cross entropy, because it has a very nice information theoretic interpretation, which I don't want to go into detail right now. But you can wake me up in the middle of the night and I can give a complete lecture about all the beauties of this definition. Essentially, it has to do with how many bits do we save, or does something cost under an optimal communication channel. And that's that is what entropy and cross entropy mean capture. And if we have a completely pure region, so only red or only green balls, right, or purple, whatever the color are of these balls, then if I grab a random ball from this region, well, yeah, you're not going to be surprised, right? I mean, that's at all. You know that it's just going to be just green, just red, just blue, right? Because that's the only type of color that we have. And hence, any ball that I draw and I show you, there's going to be 0 surprise. Are 0 bits transferred, right? Because you already knew what was coming. So hence, then the entropy is 0. Whereas if it's a completely 50-50 mix, then, well, you can't guess which color ball I'm going to grab, right? I mean, so every ball transfers maximum of information in this particular case. That is the very short description. And as you can see, the shapes of Gini and entropy, they're very similar. And in many cases, they hence perform similar. My experience, and I might be a bit biased there, entropy is a little bit better, but because it's even steeper here, and steepness is good, but okay. Okie doke. Yeah, the misclassification we basically try not to use in practice. That we'll revisit that in a second. So what does a classification tree then look like, or a decision tree classification? Yeah, it's all a bit the same. This is for the hard data, so one of our prototypical classification problems. So we first have a test, and if it's normal, we go left, otherwise we go right. Again, this is a small, cute little tree, relatively easy to interpret, right? So explainable AI, yes, absolutely. But this, if we use cross-validation, we get 6 nodes. I mean, that sounds about good. And well, using cross-entropy in this particular case. So this is the tree that you get after first learning the full tree and then pruning it back, right? And let's have a look at the unpruned tree. I mean, that's yeah, not really explainable AI anymore, right? I mean, that's this one needs to be pruned back, and this is where the entropy then came back in me to do this. So if you look, okay, so this is like, okay, if it's an abnormal, I already forgot the name of the test, but abnormal test, larger value, smaller value, and then here we have 2 bins here where the majority vote in both cases is yes. Well, why would we do that, right? And that's because whether we have a yes here, or just a yes here, we remove this node completely, there's no effective difference, right? I mean, that's in how we apply this tree in practice, right? I mean, that's it's, if anything, well, this might be a yes with an exclamation mark, like hell yes. And this is like, well, maybe yes, right? I mean, that's and exactly that. So the difference in confidence. Nora, yes, the slides actually should already be linked, but if they're not on the website right now, then I'm not going to do this right now. I mean, not maybe in the break, but if they're not linked, I will do this definitely during or after the lecture. Okay, so but from a yeah, so how can this happen that we even split it? Well, this has all to do with this Gini versus entropy, right? So from the misclassification perspective, it doesn't really matter, right? We're going to say yes anyway. But however, Gini and entropy, they like these very pure areas, right? Where we're really certain. They really want to maximize certainty. And in this particular case, this is really an artifact of that. So long story short, entropy or Gini, yay, but you really have to be careful with your pruning back because you can get these, well, weird artifacts, right? Or that may seem weird if you don't think about it more than half a second in that. So like I said, if you read this as yes, and this is hell yes, all of a sudden it makes sense, right? But then we also here have a yes, right? So basically all these three nodes, we can merge them just as easily into one thing. We can just prune away those decisions and just have a, okay, this is a yes. And if you now want to have, let's say, a degree of confidence, okay, then we can split further. Okay, good. Let me now, yeah, I need a few more minutes. I mean, that's, now we have a break. Good. Cross-validation is our friend. What I'm already going to forward reference to is that decision trees are, and I do like them. I mean, I do like to sort of mock them a little bit, but I do like them very much. One of the things that you always have to be very careful with decision trees, and why many people don't like them, is that they have a very high variance, right? I mean, that's, they have low bias, high variance. Let's analyze that. I mean, that's why would they have high or low bias? Sorry. Well, normally in the lecture I would ask for raised hands. I mean, now it's a bit more cumbersome. You can think about it. Yeah, you may raise your hand, but that's. I'm just going to give the answer. I mean, that's it's just easier this way. But the main point is that a priori we can, well, any, let's say, configuration of boxes we can have, right? I mean, that's so we don't have a particular bias towards, I mean, how many boxes, how are they placed, right? I mean, that's it's very free form. It's non-parametric, right? I mean, that's there's essentially infinitely many models that we can choose from. Yay, that's very good. However, in practice, we learn these models iteratively, right, greedily, and from limited data. It's from the limited data that we decide where to put the cut points. And as a result, well, what is variance, right? I mean, if I give you two slightly different training sets, that may lead to slightly different places where you place the cut points, right? I mean, that's just because, well, hey, put place it just to the left of this point, to the right of this point, just depending on your training data. It's a bit brittle in that sense, right? Because it makes these hard cuts. Is it larger than one or smaller than one? And it can't really say, well, yeah, okay, I made this cut because of these 2 points were here, right? I made this cut here, but now I have a point over here. It's too close to call. Maybe it's green, maybe it's blue, I don't know, right? It's too close to my decision boundary, right? I mean, that's decision trees don't give a F. I mean, that's about that, right? You're either to the left or to the right, and that's that, right? So hence high variance. Okay, we're gonna see that in action in a bit, but I want to just always already forward reference this. What we see is that, well, this is the training error for this hard data set. Training error goes down very nicely. I mean, that, so okay, we can use then cross-validation to see, okay, what is good? This is the cross-validation error. I mean, that's the brownish one. We choose the one with the one standard error or the lowest one. This is just the choice of the lowest one. And if we then look at the test error, this is green. I will also redo these figures, hopefully next year. I wanted to do this today, but I was dragged into a number of meetings, sadly. But if you look at the test error, well, the best test error is over here, but the cross-validation one is actually pretty good, right? I mean, the estimate of the generalization error. Okay, so cross-validation, once again, right? I mean, that's do buy it. Works, good. So far, I've been, well, not cheating you, right? I mean, I've definitely not been cheating on you. I haven't been lecturing any other students. I mean, but we've only been looking at simple binary decisions, right? I mean, so we have a continuous valued attribute, let's say x1, and we choose just a value lower or equal, something like this, right? So just to make a region. There was this test here, look. And so either you, well, positive test, negative test, right? And that's, okay, also a very natural binary split. What if we were to have an attribute that is categorical? So nominal, unordered, right? So let's say red, blue, or green, A, B, C, D, right? Something like that. I mean, there's no natural order, right? I mean, that's, now what you could consider, let's just keep this slide here. We could say, you know what, I'm going to split on all values at the same time, right? I mean, that's, so let's say I have red, blue, and green, right? I mean, that's, then rather having one node that splits 1, 2, it would be 1 split, 2 split, 3 split. We can do that, right? I mean, that's, because you can also interpret it as we have the main node, and then we have for the left branch, okay, I mean, is it red? Then it goes left, and then on the right hand, no, not red, right? And there you can have your next split. Is it green? Okay, if green, we go left, and if not, then it has to be blue, then we go right, right? I mean, that's, so those are two natural ways of splitting off categorical values, right? Either one by one or all at the same time. But that's a bit, I don't know, unsatisfying, right? Because maybe we don't have 3, but 3 still goes, but maybe a 4 or 5, red, blue, green, yellow, orange, right? And that's, so we have this many. And maybe red and orange, they share some information, right? And maybe green and blue as well. And what I forgot what the yellow is then the weird one, right? I mean, that's, but anyway, orange and red we would like to have combined. We can't do that, decision trees, not that easily, right? I mean, either we have to split off, I mean, first, let's say yellow and then green and then blue, and then coincidentally we have red and orange left. That's a bit unfulfilling, right? I mean, if we would like to group those two colors in one go. The problem is that for a categorical attribute, how many, if it has q values, then there are 2 to the power q minus 1 number of possible splits, because that's the number of subsets that there are, right? If you have q things, there's 2 to the power q possible subsets, and a number of those are just meaningless in that for us, because the empty set that doesn't really matter. So hence 2 to the power q minus 1 minus 1. If q is not just 2 or 3, this very quickly becomes way too many. We don't want to look at all those possible sets, right? I mean, that's, what we can do, and this is, I think it's really a brilliant trick that many people don't know, even if they use decision trees. I mean, that's, but it's really, it's a beautiful trick. What we can do, we take all of these q values, and for each of those, we're going to see, well, how, let's say, what is the proportion of labels? So in a binary classification, we have red dots, we have black dots, right? I mean, that's, okay, this is for value A. This one, well, we order them now, all of the q values that we have for this particular attribute, in descending order of purity for the one class, right? Or ascending for the purity of the other. That's what you get for free. And what we can now do is we can choose a cut point in this order, right? And that we can either say, okay, well, we just want to place here, so just at A, but maybe A and B. Let's make this now red and this orange, right? Because they share lots of information, they behave the same. So this is a natural cut point, right? And maybe this is now yellow, and yellow actually, well, it's a bit less good, right? But I mean, the 3 of those combined, and so on and so forth. So by ordering the previously unordered values based on the purity they achieve, we now turned an exponential problem into a linear problem. Because right now, under this order, it's just fine, just considering each of these, well, at most q minus 1 possible split points, right? It's really one of those tricks that when I first read it, like, wow, this is trivial. And then you start to think about it, it was actually, oh, close to brilliant. I mean, that's because in many, many practical settings, you will have unordered values. And quite often, I mean, well, often they're binary, but when they're not binary, then all of a sudden you have too many. And then decision trees become very, well, brittle and icky and unhandy and unwieldy, right? This trick all of a sudden makes them tick, and it works really well in practice. Good. All the detailed dots here, I mean, I'm going to skip for now. Let's see. Okay. I thought I would be done by now with the decision trees and we could move on. Let me take a few more minutes and then we go for the break. I mean, that's because this should not take so much time. Famous last words. One of the really things to like about decision trees is that unlike almost any other machine learning model, they are, let's say, well, inherently or almost inherently applicable to data with missing values. So what does it mean? If we have our data set, right? I mean, that's what we've so far always been assuming is that essentially every cell in our data matrix, right? So for every predictor xi, right? For every row, I mean, we always have a value. That is completely utopic. That in practice, this never happens. In that people forgot to measure something, or the sensor went batshit crazy, and it turned out not a number, or negatives where it doesn't really make sense, right? So there's going to be plenty of cells in your data, in real data, that have a value that you can't do anything with, right? I mean, that's what many books prescribe. I mean, that's the panacea. Is that okay? You know what? Ignore those values, and by either removing those columns or removing those rows. Those people have never looked at real data, because if you do this for real data, that means that all of a sudden you have almost no data left in that. So missing values are just a fact of life. In that in machine learning we happily ignore, because it's typically quite difficult to make methods robust against missing values. Like I said, decision trees are almost intrinsically suited for missing data. I mean, not like completely, but I mean not almost automatically. Why? Unlike, for example, linear regression and all its friends, where we always use all predictors, right, in one way or another, right? I mean, that's or if you have lasso, I mean, a number of the predictors, but we really need all these values. If one of those values is missing, well, lasso can't make a prediction, right? I mean, that's and typically these models, they use many of the predictors, not all, but many, right? Not just a handful. A decision tree, at every branch, it only uses one predictor. So in a way, the chances that you run into a missing data value are already much smaller, right? And if you always look at all of your predictors, and then whenever something is missing, you're going to run into it, right? And that's a decision tree. Let's actually go to one of the examples. Let's go to the simple example over here, right? I mean, that's suppose that for a particular patient, we don't know if they have chest pain, right? And that's or whether it's value B or C. That's now, if this person does not have a normal thallium stress level, right? Then we would go into this branch. Then we would have to see what is CA. I mean, is this the calcium level? I don't know, right? I mean, that's the CA level. I mean, that is the only thing that we need to know. We don't need to know whether they have chest pain. So all rows where we might not know whether people have chest pain, but that fall into this right branch, we can just handle, right? I mean, that's basically, we can just happily and rightfully ignore the missing values. I mean, ain't that sweet, right? That's okay. Now, what if that was not the case? I mean, that's if we now went to the left branch and then we're here and then, chest pain. We don't know for this particular record, right? I mean, that's if you're actually like in the field, right? I mean, that's and somebody is in your emergency ward, then probably you can ask if they have chest pain, right? If the data has not been recorded yet, but we work with static training data, we can't ask. Now, what can you do if you don't have the value for chest pain, but maybe you have something else? Maybe like, okay, is the a sensitive belly or something like this, right? I mean, that's this is my way of saying that there might be another attribute that you do have access to that you can use as a surrogate for chest pain. So if this is the tree that you learned overall, right, and this is a good tree, right, you like it, and that's then for every internal node, we can see, okay, what if this split would not be available? What would be the best alternate split that we can figure out that would achieve as closely as possible the same split of the data, right? Perhaps achy tummy, right? I mean, would be, let's say, a good replacement for chest pain. Maybe not perfect, right? Maybe some people with an achy tummy don't have chest pain and the other way around, right? I mean, that's so it would not get exactly the same split as chest pain, and that's why we chose chest pain. That's the best one. But if we can't know chest pain, okay, well then let's go for the slightly worse achy tummy one, right? And that is a procedure that, even though it's computationally not super cheap, because for every internal node, we now have to essentially find that split that doesn't maximize the overall, minimize the overall error, but maximizes the similarity between those people categorized as normal versus abnormal, right? So what are, let's say, the replacement features? And because a typical tree is relatively sparse, right? There's not so many nodes, we don't need to learn so many of those of those replacement surrogates. So we can put this to practice quite easily, right? And that's which is really sweet. It's really nice. This is the general approach. I'm going to completely skip the missing category because, well, this is so trivial. I mean, read the book. I mean, but the surrogate variables is what I just said. I mean, that's define the best primary predictor and split point based on existing observations, like the thallium level or the chest pain. And for each of those splits that you find, I mean, find that predictor and split point that best mimics the primary predictor, and then, well, find a secondary, perhaps a ternary, I mean, a third and a fourth, right? However many, I mean, let's say, the less you trust the data providers when they use your model, the more of these surrogate predictors you should provide. But typically, I mean, one or two is fine. And of course, I mean, this goes almost without saying, except that I do say it. The higher the correlation between the predictors, the better this is going to work, right? So if you have two predictors which basically encode the same thing, but measured, of course, during a different way, right? I mean, that's if you don't have the one, you can use the other one, right? You can just replace them. Okay, now just to link this up, we've learned a lot about linear regression and nonlinear regression and all that good stuff, right? I mean, that's what does linear regression believe? The linear regression believes that the data is linear. We've now learned about trees. What do trees assume? Trees assume that the world is regionally constant, right? And that's now, when is what model more appropriate? When is it better? It depends, right? It's one of those stupid adult answers, right? It depends. I mean, that's I can't say. It depends on the problem at hand. I mean, that's if your data looks like this, where green is, well, the one, let's say, class or the one type of values, and yellow the other. Yeah, this is not really a great model, right? I mean, then I would rather have this linear model. If the data is linear, it should use linear. However, if your data looks like this, linear sucks, right? Then you should use a decision tree. Right? That's much better. Do you know beforehand? Not really. No. Yeah, you can look at your data. If you have only two predictors, if you have many, what are you going to do, right? I mean, that's try both. That's sort of the adult answer there. There are more advanced answers, but that's for a different course. Good. Okay, let me wrap up trees or individual trees, I mean, advantages and disadvantages. Trees are easy to explain. You need roughly an hour for it, right? I mean, that's they arguably mimic human decision making. When this, then that, and such and so. That also goes towards the explainability. I mean, if there's too many clauses and conditions, I mean, everybody gets lost, right? However, you can depict them quite easily, and it's almost a flow chart. They can handle qualitative predictors without having the dummy variable thing, right? We can use these groupings relatively easily. We can impute or deal with missing data quite well. What I already hinted at is that they're often, it depends a bit on the setting, not as accurate as other methods. So if you use, let's say, splines and then logistic regression on top of that, I mean, that's or support vector machines, deep learning. Okay, trees are often going to be beaten, well, not to death. I mean, that's, we'll see that. We'll revive them in a few minutes. But as individual tree, too high variance will not perform so well. And well, that's what the final point, right? They're very non-robust, I mean, highly varying. Good. Okay, unless there are any questions, or actually this is my point to ask, are there any questions? So Luke asks, how easy or hard is it to choose the best regression method for a given data set? That depends on how lucky you are. If you choose the right method immediately and you have great performance, then look no further. It's almost the best answer I can give. I mean, that's typically you want to start with using simple methods, right? Such that, and if they already start, well, if they completely fail, right, linear regression, okay. Well, if linear regression works well, okay, stick to it, right? I mean, that's you know which direction to search, right? Don't go into like fully like kernel-rich regression kind of stuff. I mean, that's if it doesn't work, well, it could mean two things. It could mean that it is a hard data set. It's almost impossible to predict, right, this data set. Maybe it's too noisy or whatnot. Probably it means that you have introduced too much bias. Essentially, that your linear is too hard an assumption. Let's go to something a bit more flexible. Hence, I'm a big fan of splines. I mean, splines are very flexible, but at the same time quite controllable. If splines almost don't do better than linear, scratch your head. Probably it's a very hard problem, and there might not be much structure in the data. But, do you have guarantees? No. That's basically, you could keep on looking. And that again, in other courses, I can give more fine-grained answers than here. The moment it starts to work better, you are on the right track, right? And you can see, okay, does more non-linearity, or does more, let's say, feature selection, does this help? It's sort of like a breadcrumb trail that you lay yourself and follow. Deciding without trying out, not really. I mean, that's there is now this whole branch of AutoML, and that's basically learning to learn, right? I mean, that's can we, by seeing which methods worked well on what data sets, if you now give me a wild new data set, can I decide which algorithm is a good idea, and can I quickly parameterize it? I am personally not fully a believer in that. In certain settings, with of course, this could work if we have infinitely many examples, or if we restrict ourselves to relatively similar examples, then it will definitely work. But in my experience, in my practice, working with very different fields in medical and in material science and whatnot, no, these things don't transfer that quickly. And that, so there you really essentially out of luck. But if our colleagues in AutoML have some breakthroughs that we don't know of yet, right, or soon to make, then perhaps this part of the lecture is completely moot and outdated. Let's see. In which kind of cases would the tree be the first method to consider? For regression problems, I would not consider trees. That's basically what it comes down to. For classification problems, I would use the method I will explain after the break. Is the main or only reason to use random forests versus neural network support ease of use, basically? Ask Ravil. Yes. Ease of use and an almost guarantee that you're going to get a performance almost as well as the most finely tuned support vector machine or neural network. But again, this is forwarding already towards the second part of the lecture, because right now it's break time. However, I have some homework for you if you want. I mean, you can also do this later on. Here are the links for the evaluations. It's evaluation time. This is probably not the first course where you've been presented with something similar as this week. Official evaluation for each course always happens roughly around this time of the semester. There are 2 small surveys, and normally you have to fill them out on paper. Right now, the university joined us in 2021. You can do this online now. It's amazing. I shortened the URLs because it's a bit easier to type over. I can also dump them in the chat. Let me do that right now. So this is the link to the lecture survey. And this is the link to the tutorial survey. Okay, good. Speaking out of experience, I think this should take not much more than 5 or 10 minutes to fill out. Greatly appreciate it if you fill this out. But please do. This is the first time Professor Valera is teaching this course. So she particularly welcomes any comments, right? I mean, that's, of course, constructive feedback, right? I mean, that's, we're all human. I mean, that's, we can take critique, but I mean, try to be positive and help you, and particularly, let's say, the ones who will be taking this course after you. So for the questions specifically aimed at the lecturers, I mean, well, you can either try to think back just the lectures of Professor Valera, or just in judges together, right, as sort of one short-haired, long-haired lecturer, I mean, with different accents. We do particularly welcome in the open comments. I mean, if you have specific remarks, please do make them then specific to either me or to her, right? For the tutorials, same thing holds, except that normally you have to fill out which tutorial with whom, because we have a slightly different setup than we would have in an offline tutorial where you would only have one tutor that you would see regularly. Now you see many faces. So try to, let's say, judge the tutorial as a whole, right? And in the comment section, if you have specific comments about specific TAs, specific tutors, or the general organization, please make them there. And again, very much appreciated if you do so. Good. Let's reconvene in, well, 10 minutes, and then we continue with the forest stuff. I'm going to turn off my video and audio for now.
The plus sign on them.
Yes.
Was that by accident, or is all of decision trees additional?
No. So so plus signs are not, let's say, bonus or additional material. This is material that is, I think, better explained in the ESL book than in the ISLR book. The ISLR book sort of skims over it in that. So the missing predictor value and the categorical splitting, this is stuff in the ISLR book, it gets perhaps mentioned, but the ESL book actually explains it. This is also why, for example, in this slide here at the bottom, whoops, no, I have my laser pointer again. No, go away. So up here, I always give the chapter where you can find this. So that's what the plus is basically. This is beyond ISLR. Right, but still part of the course, and so you need to know this for the exam and for some of the assignments perhaps too. Good. Let me close my window because it's getting rather chilly. So good. Then I hope that many of you filled out the survey. It will still be online for a few more days, so if you need a night's sleep or something like that, that is still okay. Good. Then now I'm going to power on a bit because we spent too much time on individual trees, perhaps. Then again, hopefully it's now clear. So far, we've been learning always one model, right? And as you know, I mean, two heads know more than one. And this is also exactly the case in machine learning. The moment that you are going to combine the decisions or the outcomes, the predictions of not one, but multiple models, then you have created what we call an ensemble or an ensemble method, right? So an ensemble method takes a number of other methods and then somehow incorporates the decisions, and that is then the ensemble. So it's sort of a wisdom of the crowds kind of thing. Here's an example. I mean, why does this work? Again, from ESL, right? There's a plus. So you have, let's say, 50 members in a committee, right? Hey, 50 predictors, for example, right? I mean, that have to choose, I mean, who's going to win some award, right? And and as you know, I mean, well, most actors, they're better at acting than making in real decisions, but there are some actors that are perhaps a bit smarter, a bit better overview. So many of these, from a machine learning perspective, we would call weak learners. They have some opinion, they're right sometimes, but typically they don't have so much to say. Whereas some of the learners, they may be better, right? But they also make their mistakes, so you don't want to follow them all the time. Now, here you have the proportion that if there's 15 random members out of the 50, you don't really know, right, which ones, and 15 of them have some knowledge, right? So let's say who should win the award, and the rest they just do random stuff, right? Now, if the probability that these 15 people are correct, right, and if we then take the majority vote, then the green line would be the expected outcome of the prediction. I find it a stupid example with the Academy Awards. Just imagine that 35 of our predictors are just completely random, right? And the 15 that we do have, they become, depending on, let's say, the probability of being correct, they're better and better at their task, right? I mean, but overall, you see that we only get 4 or 5 correct on average, right? With quite a big bandwidth in that. That is if you just go for the individual decisions. If you do this really in a consensus kind of way, in a smart ensemble way, you actually can get much, much better very quickly, which is nice. That's what we're going to try to attain. Okay, so how do we do this? I mean, as we'll discuss 3 different methods. Those are the go-to methods. I mean, that's and the basic ones as well. Bagging, random forests, and boosting. Already in the chat, I saw a few of these mentioned. We'll go there in a second. Let's start with bagging. Bagging is the easiest one because bagging you essentially already know. I mean, if you paid attention to one of Professor Valera's lectures, you know what the bootstrap is, right? But what is the bootstrap? Well, the goal is to reduce, well, the bootstrap normally we use to figure out what is the confidence, what is the variance, what is the reliability of a parameter setting, right? I mean, that's how did it work again? We have our data set and we sample many data sets of the same size, but we've sampled them with replacement, right? So we have, let's say, 1,000 data points, and now we're going to sample new data sets of, again, 1,000 data points from the original data set. So there are going to be a number of duplicates, right? We're not always going to grab all the data points from the original one. And that's the whole point of the game, right? And we're going to do this many times, 100 or 1,000 times. And on each of those data sets, we're going to then, for normal bootstrap, estimate our variable, right? I mean, and here, what we're going to do for each of those bootstrap data sets, we're going to learn, for example, a decision tree. We could also learn another learner, but I mean, right now we're talking about trees, right? I mean, that's obviously, I mean, but I didn't point out just yet. If you're not learning one tree, but you're learning many trees, then you're learning a forest, right? For all of those who are here in Saarland, it would make you feel very much at home. So what is the purpose right now? So for normal bootstrap, it is to estimate what is the variance. I mean, how much can you rely on your estimator, right? I mean, right now we're doing this differently. We're going to be using the bootstrap and then calling it bagging, okay, to reduce the variance of our models. So as we already saw, because a tree makes this sort of like hard cut decision, right? I mean, that may just be dependent on some your data being, let's say, a little bit be held to the left, to the right, the stars are aligned. But by doing this resampling and learning a new tree for each of those resampled bags, we get a whole bunch of trees, and it's much more difficult to always make the same mistake, right? Because the data are sufficiently different. And so hence we're going to get a whole forest of trees, each of which are slightly different. And overall, the decision of the forest, the majority decision of the forest, we can typically trust much more than that of an individual tree. So just to wrap this up, generate B training data sets using Bootstrap, just sampling with replacement. On each data set, build a tree. And we're now going to read, so this is F hat asterisk B. B is the Bth data set, and then for X, wonderful notation again. And then the overall outcome is going to be this, right? So we sum the outcome for the query point over all trees that we have. We normalize it, and that's going to be the majority outcome, or the averaged outcome. Now, I said that ensembles you can use for essentially any type of method. That is true, but for some methods it's more useful than for others. And you can show, I'm not sure if we included this in the assignments this year, but for linear least square, bagging doesn't help. Well, we can show that. I mean, that's, and if it's not one of the assignments and you're bored on Sunday, I mean, please go ahead, right? I mean, it's relatively straightforward to show this. But for decision trees, it is very, very helpful in that. So what we typically do in bagging, because the variance is going to be taken care of by having many of these bags, right? Yeah, these training data sets, we don't really care so much anymore that trees are overfit. Because what we already saw in the previous slide with these, the Academy Award one, if only a few of the predictors, the learners, the Academy members have some kind of intuition of what is good, what is bad, the overall decision will quite quickly go to the right value. So we don't need to bother so much about pruning trees, right? So we just grow them deep and unpruned and just very crudely, and we just have to make sure that through bagging, the variance is reduced. Obviously, it's straightforwardly applied for regression, right? And this is the average decision over all the bagged trees. I mean, that's trivial. And for classification, we could just go for this, the majority vote, right? We just look at the argmax out of the possible labels they could predict over the entire ensemble, over the population of trees that we have, right? If most trees say red, okay, let's assign red. If most trees say blue, we say blue, right? That's relatively straightforward. Okay, does this work? Yes, that's So please be colorblind in the following way. You cannot see, or you can only see black, and you can see green, right? You don't see blue or yellow, right? I mean, that's, I was trying to redo this figure just before the lecture, and well, I didn't get this finished on time, but maybe, because we have been using this one for a few years now, and I think it's mega confusing. So the black line is what should I say? The dotted line is one tree, just a single tree, right? And that's what we can see is that with the test error, so here we have bagging. I mean, that's here we have bagging. But on the test, well, actually, if we have the right number of trees, so number of bags, we can actually reduce the error, right? Just by simply, it's not a huge amount, right? I mean, that's, but it is really on the generalization error, right? We almost always do better than just with one tree, right? Even if it's not a massive improvement. And please don't say, look, the yellow one is better. Yes, I know we get there in a few slides. Now the training error, that is the green one, right? The out of bag estimation of the error in that. So this is why you always, let's say, that the real test error is more useful than the estimate thereof, but that's a different story. Okay, good. Main message: by carefully learning one tree that is not too overfit, we will most likely do worse than just learning 100 stupid trees and not even bothering with pruning, right? That's the message here, right? I mean, that's, well, never underestimate the power of stupid people in large groups, right? And that's a powerful adage. Okay. How do we guesstimate the test error of a bagged tree? So how do we get so ideally we would like to have the black line, right? I mean, that's tricky. How do we get the green line? Well, cross-validation, right? I mean, that would be one way. Cross-validation, that, well, then for all these bags, hey, but wait a second. With bagging, what do we do? Out of all the data, we sample a new data set, a bag, right? And that's of also n data points, but we sample with replacement. That means that out of the n data points, we choose a number of them, but not necessarily all. Sometimes we choose all, right? Very rarely. That's typically we choose only 2/3. So you can actually show this. I mean, that's that on expectation you will choose 2/3. 1/3 of the data, of the original data, you will not sample. Hey, that is actually a very natural sort of cross-validationist test-train split, right? I mean, that's and this chunk of data that we didn't sample in a bag, we call the out of bag sample, and we can use it just like in cross-validation to measure how good is the tree that we trained in the bag by looking at the data that we didn't see out of the bag, right? But, and this is very easy to just while you're sampling your bags, keep track of which data points you didn't use, train your tree, evaluate it on the out of bag, and then it's a simple for loop. And that, okay, good. Then one other thing that you should notice here, I mean, I put it here as a bullet point just to, when you study that you don't forget about it. Look, number of trees goes up. Error stays flat. There's no overfitting. It's essentially, I have to be a little bit careful, right? I mean, but essentially it's impossible to overfit with bagging. More is better. It's just, at worst, it will just not improve anymore, right? So invite as many, let's say, weak learners, as we call them, let's say stupid people, but not entirely completely random, into the ensemble, and I mean, the better it gets, right? And there's essentially no harming. That was for a long time a very surprising result. Right now we understand this a bit better, but again, too much for this course. Good. Now to one of the nicest methods that we can explain today, but also that it's really one of the main methods that I would really argue to use first. I mean, that's earlier Luke asked, I mean, what is the best method for regression? Yeah, try something. Yeah, splines, my main favorite. For classification, random forests. Always try random forests first. You can also use them for regression, but for classification, they're definitely my go-to method. Well, before we explain them, let's point out that bagged trees, they have a problem. bootstrap samples, each of this, if you have this data set, right, and we sample 2/3 out of it, so that would be this part, right? Let's say for the next bag, we sample, let's say, maximally different. That would be this part, right? So we have this part, there is a very large overlap already. And that is in the best possible way, right, to sample these things, right? And that's having the expectation of 2/3. That means that each of these bags, each of the training data sets, have on expectation a very large overlap, and hence a very strong correlation. If you have learned something on the one bag, probably you will learn exactly the same thing on the second bag, and so on and so forth. So they do decrease variance because we look at different, let's say, instantiations of our data set, right? We've seen this, I mean, otherwise the curve would not go down, but they don't really do that very well, right? I mean, there's essentially too much correlation still between the samples. So let me explain this slightly differently than I have it on the slides. I mean, let me unroll it differently. Suppose that predictor X1 is really important for your, or it seems, I mean, over the whole data set, very important towards your predictor, right? I mean, not towards your label, your target. Then if you just learn one tree over the entire data, you're definitely going to first split on X1, right? I mean, that's now suppose that we're well, it may be a good thing, but yeah, high variance, right? I mean, that's why do we put the split point. Now we're going to do bagging, so we don't have the entire data, but we have these random subsamples, right? Still of size n, but I mean, now in most of those, what is going to be the most important feature? X1 probably, right? And that didn't really change. Because there's so much overlap between all these samples, what is probably going to be the split point that you choose on X1? Probably very, very similar, right? And as a result, I mean, you can essentially get as many bags as you want, but because you always look at the same set of features, and for a very large part, the same data, those trees that you learn are going to be very similar, right? I mean, that's you have to be, basically you have to hope that you got very different samples, and only then you will get sufficiently different trees, right? But until then, you're basically just repeating, you're relearning the same thing and over and over again. Now, in 2001, Leo Breiman, I mean, one of the big names in statistical learning, and especially in the more interpretable exploratory learning approaches, came up with, I think, a brilliant idea, perhaps one of the best ideas in machine learning. And the idea is as follows. Instead of using the full set of predictors, X1 to XP, right? Let's use a random subset of them, right? So we're not going to feature selection in a way where we choose the features we want most. No, we're just going to have a random subset of them. And we're going to repeat this many times. We're always going to look over all the data, but basically for every, well, not bag, right? But I mean, that's, let's say, variable bag, no, that would be very bad. No, let's not go there. So for every projection, random projection, that is better. I mean, that's a subspace. I mean, that's SAG is also not good. That's for every random projection, you then learn a tree. But if I make sure that the number of features that we randomly select is very constrained, and he suggested square root of p, respectively, p over 3, so the chances of always selecting X1, it's almost 0, right? So that means that right now, with the random forest approach, many of the feature sets will not include X1, and hence the trees that we learn are going to be very different. Hey, we're going to have variance among that, right? Or basically bias. I mean, by having a small feature set, we introduce bias, and hence the variance goes down because, well, there's, let's say, less the same type of error that we can make. Now, this trick, learning many trees over many random projections of your data, that decorrelates the trees because they really see different predictors, right? They essentially see different data. So whereas bagging tried to make the trees see different data by really selecting the data, which makes sense intuitively, Breiman said, no, we're going to see different data by just projecting it differently. And that is actually the better idea. Okay, so this is already explained. Now we go back to the figure, and now please stop being colorblind, right? And if you're colorblind, I'm going to highlight the lines that you should look at. So the blue line, that is the out-of-bag error of a random forest. So you can already see, compared to the green one, much better, right? I mean, that's the out-of-bag estimation. What's the actual test error? Well, it's not the black line anymore, it's this one now. So this is really consistently better. So by looking at random projections, you're going to get essentially a better ensemble. But, yeah, so, oops. So that so how many random forests, how many trees should you grow, right? When that well, just like with bagging, there is essentially no overfitting. But it's very hard to overfit, very, very hard. And you see that the number just so by the number, I mean the error goes down very rapidly and then it stabilizes. In that where if you have the number of predictors the same as the number if you have, then of course that would be the same thing as bagging. So, but the green one, this is the better one. Good. I'm going to skip a few of the next slides, and I think I'm going to explain. Yeah, let's do that in the interest of time because it's already 4. I'm going to. Yeah, I'm basically right now just going to wrap up directly, and the leftovers I'll do next week. But not before I share a small anecdote with you, and this illustrates why random forests. I mean, they're really a go-to method, and that's. I have some friends in well, also high places, but I mean particularly in high places at big tech firms. I mean, that's and one of them leads an AI lab of one of these firms. I mean, because we record this, I mean I have to be a bit more conservative in what I share. I mean, normally I name the person, but right now I'm not going to do that. That's but anyway, this firm consults. I mean, so it's a big firm that consults for other big firms, and essentially, many of these clients say, "Okay, oh, give us deep learning, right? I mean, give us your deepest learner. I mean, that's and do the best you can with our data." And what they almost always do first, and what is very often actually the product that they sell, has nothing to do with neural networks. What they actually do is they learn a random forest, because the random forest is going to get 99.9 or something close to that of the performance of a very carefully tweaked deep neural network, right? If you can find the right topology, blah, 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 for that particular problem. Random forest, very, very often, well, perhaps not 99.9%, but let's say 90% of the performance, random forests are just going to get, and you barely have to choose anything, right? More trees, better, right? I mean, that's how many predictors? Well, square root of p over 3, whatever, right? Just avoid too much overlap. And well, like I said, these are often then sold as, well, they're sold, of course, not as deep learning, that would be a lie, but like, okay, well, this is the best model we found, right? Oh, I mean, is it deep? Yeah, very deep trees, right? I mean, that's, so many nodes? Yeah, many nodes in the trees, right? True story, bro, really, this is true story. But so a random forest is sort of out of the box, one of the most powerful methods that we have. It's also one of the most stupid methods that we have, but yeah, so a bit like what we'll see in one of the next lectures, k-means for clustering. Random forests are one of those algorithms we love to hate. I mean, they're so simple, yet they're very, very difficult to beat. And of course, for specific instances, you can always come up with better algorithms, right? If your data has property X and geometrically and blah, 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 right? I mean, sure, if you have tons of vision data, okay, well then neural networks are definitely better. But for most problems, just throw a random forest at them and you already you're very close to what you can squeeze out of that data. So hence, I think this is a good moment to wrap this lecture up right now. And then, well, I have, 5 slides left on trees and forests. Those we'll handle then next week. So if there's any questions, I'll be very happy to answer them. And otherwise, I mean, I'm going to wave bye-bye and see you next week. Cheers.